All right. Um, we'll look at introduction to machine learning today. First, I will give you a background where machine learning came from. So that's the area, artificial intelligence. The overall artificial intelligence as an umbrella technology. Within that, we have machine learning. So I'll give you context of artificial intelligence first. Then we will see machine learning in little more detail. So first part will be little quick. So we have been hearing these terms, artificial intelligence, machine learning, deep learning, data science. All these terms we'll try to decipher, discern, separate out, understand them a little more carefully and distinctly in this session. So artificial intelligence is bringing intelligence automation. Why did I put this statement? Because if you remember, industrial revolution, we started with a steam engine that did muscle automation. Whatever physical strength that we had, now machines are able to do those physical actions. So that was muscle automation. When software came, it did process automation, the deterministic flow that was automated typically in process automation. AI is what is going to do is thinking automation. Intelligence automation is what AI is doing. Data science, because it is science of data. So wherever in applications, we are using data to train, build models and other things. So wherever data dependent applications are there and the science of data, that is data science. So there, um, we are using patterns, finding patterns within the data, insights in the data. So there is a field called data analytics, which is a little oldish but still very prevalent. This is where data science comes into the picture. The AI that we practice today is also part of data science because it is also dependent on data. But there is some part of AI which is not data dependent, not fully data dependent, that we'll also see. Okay, let us go a little higher and have a uh, uh, 30,000 feet kind of view of the core idea. What is the core idea behind what? Behind any problem solving. Why are we doing data science, artificial intelligence, machine learning, or deep learning? It is to solve a problem, right? And typically, the problems are solved in a software manner, algorithms manner. So, what is the core idea here? The core idea is given an input, we have some steps in the middle to process the input and return the output, isn't it? That's a very, very abstracted view of problem solving. We know some inputs, we know the desired output, and say how to go about it. So this is what is called as finding a function. This is actually a mathematical term, and in school and in colleges, you might have heard about it. That we are finding a function which takes input, processes it, and then gives out the output. So this is another way of saying that we are finding a relationship between input and output. Right. So how inputs are converted to output. This is also a transformation. All this is nothing but building a model. In machine learning and deep learning and in artificial intelligence, this is what is termed as building a model. Given an input, getting the desired output. I'm being very simplistic here just to progress the discussion, the session through from very simple thing towards little more difficult things. So the whole idea of problem solving, as we saw, is to find a function. Now, some functions are very simplistic. Say, I've given an example here. In summer, say ice cream sales go up, right? So as temperature goes up, ice cream sale goes up. So it's a sort of a direct proportion, isn't it? Somewhat direct proportion. So it's a cause and effect, kind of very simplistic function, simplistic relationship. And for such simple functions, which are straightforward, for which the formula or direct proportionality is sort of known, simple rule-based programming is sufficient, isn't it? But there are some functions which are complex. So the example given here is, say, what would be the revenue of a business? Right? To find out a revenue of a business, there are multiple factors that go into the picture. It's just not you being an employee of the company or the business. It is your effort, your colleagues' effort may matter, the geopolitical situation may matter, some economic situation may matter. So there are hundreds of variables that affect revenue of a business or what it earns in a business. So again, cause and effect, but the relationship is far more complex, and there are too many variables, and the relationship may not be simple proportionality. It can be what is called as non-linear. There's a little mathematical term, linear and non-linear. So too many variables, complex. For such problems which are very complex in nature, finding straightforward set of equations is very difficult. Now, this is what happens in typical research, right? That for a complex problem, people work on it for years and then try to find the equations. We saw simple functions, we saw complex functions. So another example, which looks, but although I would ask questions, but here itself I'll give answers. So there's a very known famous equation, a simple function, E is equal to mc square. My questions would have been, uh, you can just type those answers in the chat window. Here, in E is equal to mc square as an equation, what is the variable here? What is the input variable here? What is the output variable here? And what is c square here? Let's look at the answers in the chat window. Somebody is saying input is C, M and C is, M is variable, C is constant, output is E, input is M, input is C. All right. So those who said M is input variable, that's correct. Those who said C is actually, if you remember, this is speed of light. So it's a constant, at least for this equation as of now, the normal everyday physics that we practice. And E is the energy output. So here, why I took this example is, for a given equation, at least we should be able to find out what are input variables, what is the output variable, and what is the constant. That much mathematical literacy is prerequisite if you want to do AI and machine learning little later. So here, and then another question would have been, is it a linear equation or a quadratic equation? Let me just quickly ask you, put your answers here. Is it a linear equation or a quadratic equation? Or none of the above, none of the two? All right. Uh, one said quadratic, one said linear. Again, those who said linear, that's correct. Those who said quadratic, they may have to brush up again, because when it is quadratic, something raised to 2 is where it is quadratic, right? Something raised to 1 is linear. We look at only the variable. So m has power 1, so it is a linear equation. C may have any power, 2, 3, 5, 10, does not matter because it remains constant. So if some of us are struggling with this, then time to rethink. All right. So such functions we are trying to find out in the research, in normal problem solving. And now we will see, can we find functions using data? That's the topic today, machine learning, which is a data science because it is based on data. And in machine learning, we try to find out the function given data. That's the core idea. Some functions, little more complex thing. So real life functions, some are deterministic, meaning given this input, exactly this output will come. But some are non-deterministic. We may get this output, we may not get this output. So these are called as probabilistic functions. So given this situation, there is a 80% chance of this happening. We may have seen that say rain prediction, right? We get the prediction in a probabilistic form. There's a 80% chance of rain tomorrow. It's a chance thing, right? Similarly, from a given picture, I've given an example like this here. Is this tumor picture? Is the tumor benign or malignant? Benign meaning harmful, benign meaning non-harmful, malignant meaning harmful tumor. Similarly, another example which I'll take it forward. So if you are playing a chess, there is some board position here. What would be your next move? So there could be multiple moves possible, but for winning, how do you decide that if I do this, there is a 80% chance of winning. If I do this, probably 20% of chance of winning. So I'm just giving you a very high level examples. So what would be next move? So such functions are very, very complex. They are non-deterministic, probabilistic. Now, to decide the next move in a chess game for a particular board position, you need extreme expertise, right? So this is what we call as intelligence. It is not anybody's and everybody's jobs to play a real good chess. For a simple trivial chess game with your niece or nephew, that's a different thing. But you need intelligence. And how do you build that intelligence? You build by studying past games, knowing the rules, conceptually understanding what are the move patterns, and of course, studying the past games. So this is how humans build intelligence. As we said, the first part we are looking at what is artificial intelligence, and now slowly we are coming from functions to intelligence. So what is intelligence? Such complex things are considered as intelligence. There are multiple aspects of intelligence, but for this session, um, doing something really, really difficult, complex, probabilistic is where intelligence is needed. Now, we are slowly coming to artificial intelligence. So, if machines meaning software programs, also start doing such complex functions, determining probabilistic functions, showing intelligence like humans, like playing chess, this is where what is called as this is what is called as artificial intelligence. Similar to human intelligence, they also build their expertise based on studying past game. So whatever this past thing is, past experiences is called as data because data has happened in the past. Using that data, we are building understanding, building ourselves, building the intelligence, training ourselves, and then preparing a model, which is nothing but a function which will play chess. So that is artificial intelligence. We will slowly come to a definition of it, but that's the whole idea. We came from functions, intelligence, and now computer. If software starts showing the same intelligence, doing same complex probabilistic things, then that's artificial intelligence. So what is AI? This is of course a non-mathematical kind of definition, but you can have a look at it. If software, computer programs also doing what we consider as intelligent, then this is artificial intelligence. So, and intelligence has, as I said, many aspects. So, ability to think in various domains, produce something unseen, and then go on training yourself, upgrading yourself. Now, I typically take one example where, so if you have learned driving in Pune, right, say Apte Motor School or wherever, then your family, while being trained, you have gone from Alka Talkies to Deccan to Curvy Road and Powell back. So this is how you got trained. But once you are trained, can you go to Solapur and drive? Yes, right? Although the roads are very different there, but generally the, there's no Alka Talkies and Curvy Road there. But still, you are able to apply that learning in a unseen new situation. And then once you have driven, say, a geared vehicle. Can you go and drive, say, automatic vehicle or vice versa? Some different technique, different configurations. Are you able to? You can enhance knowledge. You can do car racing, different controls. That is also possible. You can enhance your knowledge. So this is one example of human intelligence while driving. Now, if autonomous driving is also done similarly way, then AI has arrived in driving in autonomous in the form of autonomous driving. All right, this is an important slide. Everybody should have a look very carefully. As I said, artificial intelligence is actually a very broad term. It's an umbrella term, overarching term, where we say that whatever we consider as intelligence, human intelligence, if software starts doing it, then it is artificial intelligence, isn't it? So that's why there's a big box shown here called artificial intelligence. And on the x-axis that I'll interpret little later, there are years. So artificial intelligence is a big term. Inside it, there is machine learning. So machine learning is part of artificial intelligence. And deep learning is inside machine learning. So deep learning is part of machine learning, in turn is part of artificial intelligence. So it's a subset relationship. What is the difference? We'll see difference in more details little later. And the focus of this session later is machine learning, of course. So artificial intelligence is, as we said, anything that is intelligent that software can do. And it started in 50s. It's not yesterday's thing or 2 years back when ChatGPT came or 3 years back when ChatGPT came. No, it was there from 1955, I guess, where this term was coined in the Dartmouth conference. Um, and then from there, in 50s onwards, artificial intelligence is there. That time, it was based on rule-based artificial intelligence, rule-based programming. The software development that typically we all do is rule-based. Given an input, we'll write rules, some expression, some logic, and return the output, right? That's the idea. So that was rule-based artificial intelligence at that time. So those who are of my generation, they would remember there was a term called expert systems. These are typically expert systems which are hand-coded, rule-based ones. But what is the difference between that and machine learning? Machine learning is data-based, not much hand-coding of logic. We'll see that difference a little later, but it is data-driven, data-based machine learning. Is that kind of AI which needs data to get trained on, to find the function between input and output. And what is deep learning? Same as machine learning. Everything that machine learning typically does, deep learning also does the same thing, except that it uses neural networks. So machine learning uses different techniques, typically statistical techniques, and some other techniques as well. But deep learning, at least for this session, we can safely say that whenever we use neural networks for machine learning related approaches, then it is called as deep learning. All right. So this is the one. Another way of looking at it, machine learning, and there is a term called generative AI, which is relatively more popular these days. So whatever, actually this subset relationship is not very correct, because there could be a generative AI and there is generative AI which is rule based also, which is machine learning based also. which is deep learning based also. So it could be actually the whole horizontal thing. So there are two types of AI. One, what is called as generative AI, where we generate the answer, sometimes word by word or whatever, another ways. So we generate the answer. So what is non-generative AI then? It is what is called as a discriminative AI, which analyzes only input. It does not generate out, it analyzes the input and gives the output. That's it. It does not generate like word by word or sentence by sentence. So that's the difference. This is another important slide. Now we are coming closer to what's actually machine learning versus the typical rule-based traditional programming. The difference is evident here. In traditional programming, that is rule-based programming, we give input. Here it is mentioned as data. We ourselves write program, meaning logic. Input has come, we write the logic, how to process it, and return the output. This is the traditional way, rule-based way of doing programming. This is again, if you can see, it is finding a function. The function is written by us. The logic is written by us. Machine learning is very, very different than this. Here, what we give inputs as well as outputs and let the computer figure out the logic, the program. So you all should understand this dramatic difference. So that's why machine learning is heavily data driven, data based. Even the output has to be given. There are subtle differences which we'll cover a little later. But if you can see, the traditional programming is very, very different than machine learning. All right. Now we'll go to some subtypes within machine learning. These are the famous ones: machine, uh, supervised machine learning, where we give inputs as well as desired outputs to the program and the logic gets built. Now, as we said, data is nothing but whatever happened in the past. So for supervised learning, we have to give past input and past output, corresponding output. Such data has to be fed to machine learning algorithm, and it generates the model, meaning the function between input and output, the relationship, the transformation between input and output. Another type of machine learning is unsupervised, where inputs are given and not outputs, because there are not outputs in such situations. I'll explain with examples later. Only inputs are given. So it does not really find the correlation, the transformation between input and output, because output is not given. It only tries to group the cluster the input within itself. So wherever we need grouping, unsupervised learning is used. We'll see some examples later. Reinforcement learning is little different. It goes on penalty and reward kind of thing. So no heavy data is used, but you just have to specify if you go this way, it is good. If you go that way, it is not good. So rewards and penalty, that kind of functionality has to be provided, and then it learns. This is typically seen in in games. The chess example that is just mentioned a while back, it is typically done using reinforcement learning, because the final goal is to win, to capture the king, and which move is getting me closer to that final game, because every move will have some reward, some penalty as far as the final goal is concerned. This is what is covered in reinforcement learning. So these are the types of machine learning where data is needed, but in different forms. Why machine learning? Because, as we said, for very complex and non-deterministic functionality, we need AI, and that is, as it is data driven, we need machine learning. The first reason that I've given here is problems with high dimensionality. Dimensionality meaning actually variables. So if there are large number of variables in the problem, like predicting rain tomorrow, There are hundreds of variables affecting whether it will rain tomorrow or not. So that kind of problem with high dimensionality, machine learning is very, very suitable. Doing something of that kind with rule-based programming, you will need hundreds of researchers doing that, right? And that used to be the case before. But now with data, you can just feed it to the machine learning algorithm and it will learn the correlations between these hundreds of variables and the output. Output is whether it will rain tomorrow or not. As I said, next one, it is hard and very expensive to put people on it, rule-based programming on it. The third statement is very, very crucial, where we are saying that typically machine learning and specifically neural networks is where they are saying that they can model any function. Any meaning, whatever the relationship between the input and output may be, however complex it may be, neural network can model that relationship. It is a wonderful statement, but the caveat or the secondary clause here is given enough data. So if you have lots of data, input and output, millions of records, then it is possible to get very, very good results given enough data. And of course, why we are learning machine learning? Because there is money. We get job, we get money. Why now? As I said, machine learning and deep learning in the three boxes we have seen, it is data driven. And now data has started coming into picture in last 1 or 2 decades only. In 1950s and all, data was very, very less. Because why it is coming now? Because of internet. All of you are using social media, or there are hundreds of sensors everywhere. Even in our cars, we have sensors, the cameras and everything. So we are flooded with data. It's what is called as data deluge, the storm of data. Because data is available now, machine learning and deep learning has become relevant and possible actually. Another few reasons that why we are doing machine learning and deep learning now is to process that data we need a lot of computing power. In previous days, in my generation, we used to have one computer at least as a student for a batch of 30 students. So that era is gone. Now we have everybody has at least one machine with that person, but we are not limited to our machine or the RAM that we have. If we are able to connect to cloud, we have access to hundreds of machines, right? Depending on the budget that you have. So increasing computation power. Another reason is a lot of frameworks are available and many of them are open source, free to use. Like for machine learning, we have scikit-learn. For deep learning, we have TensorFlow, PyTorch. So many algorithms are available. And the last reason is as there is a lot of data and it is hard to process it rule-based way, manual way. Machine learning is the choice. Rather, is the only choice, if I can say so. That's why there is increasing support from industries why we should do machine learning. So I won't go through this. This is how things have evolved. As I said, 1950s and 80s. So a lot of technologies have been developed. All right. Some relatively new things. All of us must be aware of this. What's going on? All right. Okay. Some real world stories. These are some of the examples I've quoted with some references here. Now I wish to go to really one core example of actually different types of machine learnings, their examples, and one core example end to end, so that all of us understand exactly what is machine learning, at least with one example. All right. So these are some of the examples that we have seen, or we see rather every day. All right. Another little social issue. Um, if it is able to model any function, right? Then is it really going to do it? Is it magic? Is it something else. If it is able to do anything and everything, is my job at stake basically. So that's the threat people have. Some people, of course, see it as threat, and that's not wrong also. All right. My take on it is generally for AI, AI is going to be a tool that will assist us more. In very, very a small portion, it will probably replace completely, but in most situation, it will assist us. It will augment us. All right. There are still many problems with AI, and these are some of the limitations. So, and then one of the major limitation is, of course, understanding the space, the geometry, understanding some other senses like touch and smell and taste is still not that much available. So, next we will uh, dive deep into machine learning. Here are some of the aspects which probably I'll let you read quickly. All right. So some summary of the first portion, what is, quick introduction to artificial intelligence. If you have clear rules, deterministic, everything simple, traditional programming. If you need pattern recognition between input and output, there we'll need machine learning and data is available. Actually, if a little bit more data and if neural networks are used, then deep learning. And if you need generative kind of output, then generative AI. This is again very rough way of saying things. All right. This is a little funny looking statement, but very profound statement if you think about it a little more deeper. All right. Now I will move to machine learning. All right. One example which is a little funny in the sense, see, if you are applying or going for an exam, there are two ways to prepare for an exam. There are some guys who read a lot of books, they understand things conceptually and try to apply that in the exam. But there are other set of people who actually go and just solve past papers, assuming that the same pattern will come in the exam. So, machine learning, in my opinion, is similar to the second part. Okay, we are trained on the past data, hundreds of past papers, and then it is able to solve if the similar question arises. If some random odd question arises, then it will also fail. So that's how I gave this example. The last month preparation, last week preparation kind of guys, they are doing similar to what is machine learning. Okay. Now there are some rigorous definitions here. Now, if you see, learning in general is a process by which system improves performance from experience. Experience meaning past data. So what is machine learning? If the system is able to improve its predictions, its conclusions, its output generation with more and more data, more and more experience, then that is machine way of learning things. So what is machine learning? Some definitions here. Machine learning is a type of artificial intelligence. As you said, it is a subset of AI where it learns function without being explicitly programmed. We are not writing logic. Only input and output is given and it figures out the logic. And it can grow. Second characteristics is also very important. It can grow and change when exposed to new data. So you have already built a model, meaning a function, based on this much data. Now next day new data comes. If we were to do rule-based programming, then somebody has to sit and look at the new data also, then figure out is the same logic working or not. Very, very complex thing, right? But in machine learning, just add that data and retrain the model, right? So it now understands the new function. So other few definitions are given here, but that's the core essence that it is learning the function, input and output relationship without being explicitly giving the rules. And second thing, it grows, it gets trained, it gets better with more data. So, all right. We have seen this a bit. In an equation, we have independent variables, the x's and the dependent variable y. Okay, let's take one example. Say if you want to predict sales. So you are a company, you want to predict sales, and the input variables given are if I, the advertisement budget. So if you allocate this much to TV ads, radio ads, or print, meaning newspaper ads, right? Given these budgets, I have to predict how much sales will I get, say next year, whatever. So what are the variables here? What are the inputs here? These three budgets, right? TV, radio, and print. And what is the output variable here? Sales, right? Sales. So the rule-based way of programming or finding, solving this problem is somebody will sit who is a domain expert. He'll say, oh, this much weightage is given to TV, this much to radio. So it will be a1 x1 plus a2 x2 plus a3 x3. A very simplistic equation. This will be equal to sales. This is a typical way of rule-based way of solving. Somebody has to come up with the equation first by R&D, and then we'll program it. The machine learning way of doing things is from past years, we'll collect the data of these three variables and the output. So the budgets of TV, radio, and print. And then what was the sale? Next year, these three budgets, what was the sale? Next year, these three budgets, what is the sale? So this is how, if we feed the data, then it will try to find out the relationship. How much weightage TV budget has on sales, plus radio budget has on sales, something like right? Getting the idea? This is how machine learning way of solving things happen. Another example. So your salary or income, say it depends on your education, how many years of education that you have, probably say after 12th or after bachelor's, and then number of years of experience. So from after 12th, assume that everybody does 12. So 4 years of education and 5 years of experience, right? That will determine my salary, right? Or income. So if I have 2 years of education and 10 years of experience, or 1 year of education and 1 year of experience, the second guy will get less salary, right? That's the idea. So typical simple equation to model this would be this. But the machine learning way of solving this problem would be you have to give a training data, education column, experience column, and the salary column. Then given that, it will find out a simplistic equation, at least in one case, what is called as linear regression, which we'll see later. These constants, C, beta 0 and beta 1. So if we are able to find out these weights, then the equation is known. Then what happens? For any unseen case, for any unknown person, if he has 3 years of education and 5 years of experience, we are able to predict its salary, his or her salary, right? That's the idea. Once we know the function, meaning C beta 0 and beta 1. Once we know this equation, then that's the model. That's the function we have arrived at using the past data. Once this equation is known, we can use it for any unseen case, isn't it? That's the machine learning. This is the idea I have to drive you through. This is the way functions are seen, meaning models are seen. All right. Same slide. I would repeat. Traditionally, you would find the equation by research or something, but in machine learning, you just feed the data and let it find the equation, meaning what? C beta 0, beta 1. In that simplistic example. All right. This is a machine learning process. We'll now take one little funny example and one little more serious and mathematical equation example. All right. Huh. Now, this is not exactly machine learning, but it will give you a sense of machine learning. Okay. So if you can see, this is a puzzle where there are 8 examples, and we have been given 3 numbers on the left, say 2, 4, 5 in the first example, and the right hand side is the output 3. So 2, 4, 5 are the inputs, 3 is the output. For the second example, 5 to 8 are the inputs, and 2 is the output. Similarly, others. Now the puzzle is you have to put mathematical signs in between, meaning plus, minus, multiplication, and division to arrive at the output. So you have to just juggle these 4 signs, put them in such way that the output comes. This is very, very similar to machine learning. This is not exactly machine learning, as I'm saying it again. Imagine we had that income equation. So we know education, we know experience, and we know the salary for, say, hundreds of people. There we have to find C beta 0 and beta 1. Similarly here we are putting the signs. How can it be solved? It can be solved brute force. Brute force meaning try everything. Have 2 for loops or whatever, 3 for loops, and then try all the cases. Which one works? It may happen that in some cases, only 7 will be okay with these 2 signs, not the 8th one, but that's okay. Right? Most of the answers should come from these signs. Similarly, in our salary case or income case, we should find such C beta 0 and beta 1 so that most of the training examples adhere to it. They are solved by this closely, sort of, isn't it? That's the idea of machine learning. So letting computer work and find out those signs or relationship between. As we saw, unsupervised, supervised. Okay. Now we are coming little in core now. So machine learning, there is supervised learning and unsupervised learning is what. There is a third one, which I'm not showing it here, because reinforcement learning. We'll focus on these 2 parts. Supervised is where we give inputs as well as outputs. So in supervised learning, we have typically 2 types, classification and regression. I'll give you examples. Say, with these input variables, the output is yes or no. This is called as binary classification. Whether it will rain tomorrow or not. Given this temperature, pressure, humidity, these are input variables, whether it will rain tomorrow or not. That is binary, yes or no. So such problems, because we are giving input as well as output, this is the classification approach. What is regression? Actually, similar thing. You give input and output in as supervised, but the output is of not category type, meaning A, B, C, or something like that. Not like an integer, but it is a float. It is a continuous variable. It's not a discrete variable. Like in classification, it's a discrete variable. In regression, it is a continuous variable. What's the example? Say house price prediction. There are 2 bedrooms, this is square footage, and then house price is 41.2 lakhs, right? If there are 5 bedrooms, and then whatever, 10,000 square foot, probably 1.3 crores, something like that, right? So it's a the output here is not category A, B, C, D, but it is a float value. It is a continuous variable. So these are regressions. Both are supervised, classification and regression. Unsupervised, as I said, only input is given. There is no output. In such cases, only grouping can be done. We'll say one example. So given only set of people, say there's a class of 60 people. Can we group them into two teams? This is what we used to do, right? While playing cricket, you come here, you come there, you come here, you come there, whatever, you go there, something like that. You form two teams. There is no output here. You just do within yourself, within input variables only, grouping. It can be two groups, three groups, five groups, whatever. So this is what is called as unsupervised. All right. We'll take one example now. All right. Same example we'll take. This is now a supervised and regression type. Okay. All right. So this is the data set. As it is a supervised machine learning, we need training data where we have input variables as well as output variable. Now, as you can see, this is a non-Indian data, US data probably because as you can see the sales prices in dollars. So the training data here is number of bedrooms, square footage, and neighborhood. These are input variables, input columns. And the output is we are predicting the price of a house. So house has three variables. Each house is characterized, represented by three variables. The number of bedrooms, the area it has, square footage, and the locality, the neighborhood. Isn't it? Now you'll probably see uh, all the all the machine learning is actually mathematics, right? We have to put them in equation. What to do with the strings? The neighborhood is given in the words. How do you convert words into values per se, into integer-like values or float-like values? So probably that will cover a little later. For now, we may ignore it also. We can assume only two columns, bedroom and square footage, giving sales price. Now, the top table that you are seeing is actually the training data. It is not as small as shown in this academic example. We have thousands and thousands of such examples. Then only we will be able to get good results, good accuracy prediction, good accurate prediction of the sales price. And what is the last second table that I'm showing? This is the unseen example. Once we build model, once we arrive at function, given the top five rows, 5 houses, we'll come up with some function, right? Some function similar to the income function that we had seen. Once the function is known, then we can apply it on the last unseen example. Given three bedrooms, we'll put that in that equation, right? The weights would be known by training. Three bedrooms, square footage, this, the sales price is predicted. That's the application of machine learning. We get trained on the training data first. We get trained and output a model. Output a model meaning a function that has all these input variables along with its weight, at least in linear regression. There are other methods to arrive at a non-linear equation. But for now, let's consider linear equation. Once the weight is known, function is known, the model is known. That model is used to predict the unseen cases. I hope the idea is clear. Once you take this idea, then it will be a good thing because this is the fundamental of machine learning. All right. So this is supervised learning. We know in the training data how much we know inputs as well as outputs. And then the machine learning is trying to find out the relationship, the function. How does it do it? Okay. If if you have to do it traditional way, what would you do? You will probably go to some real estate agent or a broker. That guy has good idea because he's been there in that industry of say selling houses or renting houses. uh, that he knows for this number of bedrooms, for this square footage in this locality, say Kothurud or Shivajinagar, this would be the price. So he knows that logic in his brain. So if you ask him what's the logic, how do you arrive at it, he'll say something. So traditional way of solving this problem is for these input variables, as you can see, this is like a Python function. That if three input variables, whatever that real estate agent says, broker says, I'll put it as a logic, right? I'll hand code it and return the price, isn't it? So there is, so, but you will wonder how does he or somebody arrives at this number, right? If you can see, these are nothing but weights. In the final equation, something multiplied by a number of rooms, something multiplied by square footage, and something multiplied by neighborhood. Neighborhood probably will ignore only these two. That gives me the price. So the whole idea of coming out with these weights is the goal of machine learning. How do you do that? All right. So the idea is, given many examples in training data, we have to come out with the equation. This is what line number 2 says. How do you do that? Right? So we have to assume that weight wala equation, weight equation. All right. So assume that actually there is a library. Nowadays you don't do it. All these training examples, number of bedroom column, square footage column, and the price column, you feed it to scikit-learn library called linear regression, and it gives you weights directly. You don't have to do it. So how does it look? It will look something like this. So now the question is, how does it get? How did it get these weights? You can see these constants and weights. How did it arrive at those weights? So we'll see a little interesting procedure with which it arrived at these weights. Okay, and this is the core that happens behind linear regression, one of the machine learning algorithms. All right. So how do you arrive at these weights? Simplistically, you assume. So what's the equation? Price, sale price is A1 number of bedrooms plus A2 number of square footage plus A3 neighborhood, right? So A1, A2, A3 are nothing but weights or coefficients. So what we do, we start with some random weights. Here we are starting with 1. So A1 is 1, A2 is 1, A3 is 1. Everybody okay? We don't know weights. This is what we want to find out. A1, A2, A3 or weights is what we want to find out. But it's so how do we start? We assume that they're 1, 1, 1. Of course, they are wrong. But we'll put them in equation for all cases, right? And then predict price, isn't it? Or wrong weights, wrong coefficients will give me wrong price. But that's okay. At least to start with. Okay. So what will happen? So for uh, say house number 1, my guess with weights 1, no, weight 1 was wrong. But still, I have some guess, no? And the actual sales price. In the green column, I've shown in training data what is the actual price for house 1, house 2, house 3, house 4. And my guess, which is the wrong one, because the weights are just 1, 1, 1, which are wrong weights. Then how do I proceed? So I have, because of wrong weights, I have got wrong prices. Now the whole idea, this is the core idea behind machine learning. Now I am off, OFF off by the actual numbers. My guess numbers are wrong. So there is a difference between them from the correct ones and the wrong ones. Can I adjust my weights? Can I adjust my A1, A2, A3 in such a way that this difference is minimal? I will repeat, this is the goal of training, training machine learning model. There is a difference because of wrong weights to start with. How do I adjust A1, A2, A3 in such a way that this difference is minimal? then the weights with which this difference was minimal close to zero, that's the equation, right? A1 x1 meaning bedroom plus a2 x2 x2 meaning square footage plus a3 x3, and I have got such nice weights so that the difference is not there, meaning whatever I'm predicting with that equation is arriving at a sales price. That's the core idea of machine learning. All right. So as I said, so there's a difference. So can we just add the difference? No, because some things are more, some things are less. So some things are positive differences, some things are negative differences. So if you just add all of them, then there itself it may turn out to be zero or very small. So we are saying this is the difference, we square it and then average it. So this is the error we wish to minimize. There's a method called gradient descent. Okay, you have to take derivatives and then find out the direction of change and adjust the weights so that we arrive at this. So assume that we just have two variables. This is the variable and this is the variable, and this is the plot of the cost, meaning the J function. Okay, now we have to adjust these variables, weight 1 and weight 2. This is a 3D figure. So two inputs and Z is the output. X and Y is the, at least here, X1 and X2 I should say. And this is the Z variable. Idea is to come up with this point. If you all can see the where the cost is minimum or almost zero. So such weights is what we are trying to find out. Currently, the weights are probably 1 somewhere here. So this point may be 1, 1, where A1 is 1, A2 is 1. We have to come up in such a way that we arrive at such two weights where the total cost is minimum. This idea is called as back propagation, changing the weights so that, or gradient descent, changing the weight so that we come descending to arrive at a minimum. This is a minimum minimization problem, minimum finding problem, minima finding problem. So we started with 1, 1, you got some error. Error is shown on the plot, the surface. What we do, we typically take the tangent, actually derivative. First derivative, it gives you direction. And then we change the weight. I'll show you the equation and adjust the weight. Then again we take the direction where to move, where to move, meaning in which direction to change the weights. So do I reduce a1 and a2, a1 and a2? This is how I reduce both of them in the direction, so that in the direction where cost is coming down. In one case we arrive at such a1 and a2 where the cost is minimum. If we change a1 and a2 further, then we can see that cost again starts increasing. So we stop now. So once we get the minima of the cost, that A1 and A2 is the final A1 and A2. All right. So this is the equation. I'll explain again. We saw one equation where J was the cost. We take the derivative of a function, meaning derivative at a point in a surface gives the tangent direction. A little bit geometry, school geometry. It gives you direction where to change. There is some amplification factor. And then what we do, the current weights minus, if we slightly move in that tangent direction, that weight will give me updated weight. This is how I go on doing till the time the derivative is almost zero, meaning parallel. So this is how we go on updating. Here theta is weights, and J is dependent on theta, theta meaning weights. Will go down, 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 down. And at one point, theta, the updated theta and the current theta does not change, meaning weights do not change. This is where we arrived at minimum J, minimum cost. We don't have to be bothered about all that mathematics. We have what is called a scikit-learn. We will, this is how, this is what. 20-line program, 10, 20-line program, given a housing data. It is read in pandas data frame. You have these X column names, Y column names, give that data, and just one call model fit given X and Y. All the calculation that we just saw was there. And then once the model is fit, ready to be used, you just predict using unseen X prediction. That's it. Whatever we saw, all that as mathematics is given in this one fit function. That's about it. So this is what I wanted to show all of you. All right. So we started with introduction to AI. Within that, we started with functions. Then we moved to database, the difference between AI, ML, and DL. We focus mainly on machine learning, supervised, unsupervised, and that too one part of supervised called linear regression with the house price prediction example. That's about it. So this is what I wanted to cover.